Okay, so in this video, I'm going to give you a few more examples of convolution. So in this example, we consider three independent variables, and this table gives you their probability mass functions. So you can see actually the three variables have different distributions. So you can see for x1, the probability mass function is given by this, and then for x2, given by the second column here, and for x3, it is given by the third column. So you can see if you add up the numbers across each column, okay, so the sum is 1. Okay, so now we want to find the probability mass of the sum x1 plus x2 plus x3. Okay, so this is convolution because we are adding up independent variables, although they are not identically distributed. Okay, so to find out the distribution of the sum S, okay, so we first consider the sum of x1 plus x2. Okay, so to apply the technique of convolution, we need to add up two variables at a time. So we first consider adding up x1 and x2. So here I set up a table like this. The two columns here are just copied from the previous table. And then the last column is the probability mass of x1 plus x2. So actually this column is very easy to compute. All you need to do is to find out all possible combinations of x1 and x2. For example, suppose I want to find out the probability of x1 plus x2 equals 1. Okay, so the second row here, so this is the probability that x1 plus x2 equals 1. So actually, there are two possible combinations of x1 and x2, either 0 plus 1 or 1 plus 0. So the probability is just the sum of the probabilities of these two events, okay, 0 plus 1 or 1 plus 0. As another example, suppose I want to find the probability that the sum is 2. This time, again, there are two possibilities, either 0 plus 2 or 1 plus 1. You might say, well, actually there's another possibility, which is 2 plus 0. But x1 equals 2 has probability 0, so that's why the third term is 0. And you can continue, so the sum can be 3. Okay, so the only possibility is 1 plus 2. Okay, so 1 plus 2 will be 3. Okay, so now we know the probability mass of the sum x1 plus x2. Now we can repeat the procedure, this time apply it to x1 plus x2 and x3. Okay, so we consider the convolution of x1 plus x2 and then x3. Okay, and then so this time the table is similar. So here I take this as an example. So this time I want to find out the probability that the sum S equals 2. Okay, so there are three possibilities this time, either 0 plus 2 or 1 plus 1 or 2 plus 0. And then we can get this 0.245. As another example, suppose I want to find out the probability that the sum is 4. So this time there will be a lot of possible combinations. For example, 0.21 plus 0.25. What is this? This is 2 plus 2. And then 0.02, 0.205. This time it is 3 plus 1. And then 0.32, 0.25. This is 1 plus 3. Okay, so actually there are two more, actually 4 plus 0 or 0 plus 4. But the probabilities are 0, so we don't include it in the sum. Okay, so we can find out the probability of the sum by considering all possible combinations of the two variables. Okay, so this is how we can perform convolution for discrete variables. So we don't need to do any integration. So here is another example. So this time we consider the aggregate sum S. Okay, so here X are IID, normally distributed, and it's discrete. Okay, and the probability mass function is given by the table here. Okay, and then we define S to be this aggregate sum. Okay, so we can interpret, remember, we can interpret this N as the number of payments, and the x are the amount of payments. And then we want to find out the probability that the S, the aggregate sum, is greater than 100. Okay, so to solve this question, we need to first find out the distribution of S1, S2, and S3. Okay, so S1 is just x1, and then S2 is x1 plus x2, S3 is x1 plus x2 plus x3. So you can see S1, S2, S3 are not aggregate variable, okay, because they include a sum of IID variables, but the number of terms in the summation is deterministic, 1, 2, and 3, rather than random. So in the sum S here, the number of x included in the summation is random, but here it's not. So x1, S2, S3 are very easy to find out because each x is normally distributed and they are independent. So we can easily find out the distribution of the sum. Okay, so they are still normally distributed. So now to find out the probability that S greater than 100, we condition on the value of n. So n can be 0, 1, 2, 3, and then probability n equals n. And then this is S capital N, or S greater than 100, given capital N equals n. Okay, but given n is n, as the aggregate sum becomes Sn. Okay, so this is a standard technique. We condition on n, the number of variable x to be included. Okay, and then condition on n equals n, the aggregate sum S becomes either S1, S2, or S3. Okay, so the probability mass of n is given 0.5, 0.2, 0.2, 0.1, and they're here. Okay, and then we also write down the probability that each S is greater than 100. Of course, when n is 0, S0 is defined to be 0. So probability 0 bigger than 100 is 0. So that's why we have 0 for the first time. And then for these three probabilities, we can use the normal table. For example, suppose I want to find the probability S3 bigger than 100. I know that S3 is normally distributed like this. So what I can do is to standardize both sides. I subtract the mean and then divide both sides by the standard deviation. And then this standardized S3 is normally distributed. And I want to find the probability that this standard normal variable is greater than this point. So basically, I'm finding the total area of the shaded region. So you can find out the area of this region from the normal table. And this is how you can compute this probability. So anyway, these three probabilities can be computed using this kind of technique and using the normal table. And then we can find out the answer to be 0.4. Okay, so here is another example, again involving the aggregate sum. Okay, so here, similar to the previous example, the distribution of n is given, and then x are IID, and this is the probability mass of x, which is discrete. N and x are independent of each other. And then we want to find out the probability that S, the aggregate sum, is greater than 3 times the mean. So we first need to find out the mean of S. Okay, so we know from the previous lecture, the mean of S is just the mean of n times the mean of x. The mean of n and the mean of x can be computed easily from the two tables here. So we can find out the mean of S to be 1.33. So that means we want to find out the probability that S is greater than 3.99. Okay, and then if you look at this carefully, each x can be 1 or 10, and the number of x in the sum is either 0, 1, or 3. So you can see S can take values 0, 1, 2, 3, and then the next possible value will be 10. The next possible value will be 10. So S greater than 3.99 is just 1 minus these 4 probabilities. So how to find out these 4 probabilities? Well, we do it by first principle. For example, how to find out the probability that S equals 0. So this S will be 0 if and only if this capital N equals 0. Okay, so that's why this is 0.5. How about S equals 1? If you want the sum to be 1, N must be 1. Okay, and N must be 1. And then the only x in the summation must be 1. Okay, so this fx star 1 is the probability mass of one single x. So the product will be 0.4, which is here, times 0.9, which is here. Okay, so this is 0.36. How about s equals 2? Well, think about it carefully and you will see that s cannot be 2. S cannot be 2 because x is either 1 or 10 and n is 0, 1, 3. N cannot equal 2. So that's why the probability that s equals 2 is 0. And then s equals 3. So this time n must be 3. So in this case, s becomes x1 plus x2 plus x3. And then each of these 3 xi must be 1. Okay, so that will be 0.9 to the power 3. So this is 0.9729. So the answer will be 1 minus the sum of these 4. So it will be 0.0671.